There is a farmer in Kansas who has been planting wheat on the same land his grandfather plowed in the 1940s. Same soil, same seeds, same month every year. But the rains that used to arrive like clockwork in March, the rains his grandfather could plan around, that his father could plan around, that he planned around for the first 20 years of his own farming life, stopped arriving on schedule about a decade ago. Some years they come 6 weeks late. Some years they don't come at all. Some years they come all at once in a single violent week that floods the planted rows and washes the topsoil into the creek. He doesn't know why the pattern changed. His neighbors don't know either. His county extension agent talks vaguely about shifting weather patterns and climate variability, but nobody has told him the full story. Nobody has explained that the reason his grandfather's rain calendar no longer works is because something enormous, something happening thousands of miles away at the top and bottom of the world, has been quietly dismantling the atmospheric systems that made his way of life possible. The ice is melting, not slowly, not gradually in ways that science will only measure in a century. It is melting now at a pace that is rewriting the rules of global weather in real time. And the communities, the economies, the agricultural systems, and the infrastructure that billions of people depend on were built around weather rules that no longer apply. Nobody is ready for what comes next. And almost nobody understands why it's already here. The scale of what is happening to the ice at the poles is genuinely difficult to communicate in human terms because the numbers are so large they resist comprehension. The Greenland ice sheet, the massive body of ice sitting on top of the world's largest island in the North Atlantic, contains enough frozen water that, if it melted entirely, global sea levels would rise by approximately 7 meters. That is 23 feet. It will not melt entirely in this century, but it is losing mass at a rate that has accelerated dramatically over the past 3 decades. In the 1990s, Greenland was losing approximately 33 billion tons of ice per year. By the 2010s, that number had risen to approximately 250 billion tons per year. In recent years, the annual loss has exceeded that. To put 250 billion tons in physical terms, that is approximately 1 million tons of ice every single working day of the year, pouring as meltwater into the North Atlantic Ocean. Every day, without stopping. Antarctica is losing ice at a similarly accelerating rate. The Antarctic ice sheet holds enough frozen water to raise global sea levels by approximately 58 meters if it melted entirely, a number so catastrophic it belongs to geological timescales rather than human ones. But the edges of the Antarctic ice sheet, particularly the marine ice sheets of West Antarctica and the glaciers of the Antarctic Peninsula, are losing mass at rates that alarm even veteran glaciologists who have spent careers studying polar ice. The Thwaites Glacier, sometimes called the Doomsday Glacier in science journalism, a name the scientists who study it find sensationalist but not entirely inaccurate, is a glacier the size of Florida, sitting in West Antarctica, whose base is in contact with warming ocean water. The warm water is eating the glacier from underneath in a process called marine ice sheet instability, and the concern is that once a threshold is crossed, the retreat of Thwaites could become self-reinforcing and irreversible on any human timescale, eventually contributing more than half a meter of global sea level rise on its own. The scientific debate is about the timeline, decades or centuries, not about whether the process is underway. But sea level rise, as consequential as it is only one of the ways that polar ice loss is reshaping weather and human life around the world, and in some ways, it is not even the most immediately disruptive. The story of how melting ice changes weather patterns on the other side of the planet, how something happening in the Arctic in winter directly influences the farmer in Kansas, the monsoon in India, the drought in the Mediterranean, the flooding in Bangladesh, is the story that most people have never heard, and it is the story that explains why nobody is ready for what the weather is becoming. Start with the Arctic. The Arctic Ocean is normally covered by sea ice, a floating layer of frozen seawater that expands in winter and partially retreats in summer. This sea ice has been declining dramatically. Arctic sea ice extent in summer has decreased by approximately 13% per decade since satellite measurements began in 1979. The oldest, thickest ice, the multi-year ice that used to persist through multiple summers, has declined even more dramatically, replaced by thinner first-year ice that is more vulnerable to melting. In September 2012, Arctic sea ice reached its lowest recorded extent in the satellite era. Recent years have continued to set records at the low end. Scientists who study Arctic sea ice now regularly discuss the possibility of ice-free Arctic summers, meaning the Arctic Ocean essentially clear of sea ice in September, within the coming decades, an event that has not occurred in at least the last 100,000 years of Earth's climate history. The loss of Arctic sea ice matters for global weather through a mechanism that starts with a simple physical fact. Sea ice is white. It reflects roughly 80 to 90% of the sunlight that hits it back into space. The dark ocean water beneath it absorbs roughly 90% of the sunlight that hits it. This difference in reflectivity, called albedo, is one of the most powerful feedback mechanisms in the climate system. When sea ice melts and exposes dark ocean water, the ocean absorbs far more solar energy than the ice would have. That absorbed energy warms the ocean further, which melts more ice, which exposes more dark water, which absorbs more heat, in a self-reinforcing cycle that climate scientists call the ice albedo feedback. This feedback is a primary reason why the Arctic is warming at 3 to 4 times the global average rate, a phenomenon called Arctic amplification, and it is the foundation of the chain of consequences that reaches all the way to that wheat farmer in Kansas. The Arctic warming disproportionately fast relative to the rest of the planet means that the temperature difference between the Arctic and the tropics, the temperature gradient that drives the jet stream, is shrinking. The jet stream is a high-altitude river of fast-moving air that circles the northern hemisphere, and its behavior is one of the most important determinants of weather patterns across Europe, North America, and Asia. A strong jet stream, driven by a large temperature gradient between the cold Arctic and the warm tropics, flows in a relatively straight, fast band around the hemisphere. It keeps cold Arctic air penned up in the far north, it moves weather systems through efficiently, and it maintains relatively predictable seasonal patterns across the mid-latitudes where most of the northern hemisphere's population lives. But as the Arctic warms faster than the tropics, the temperature gradient weakens and the jet stream weakens and becomes more prone to developing large, slow-moving meanders, dipping far south in some places, looping far north in others, and sometimes getting stuck in those positions for weeks at a time. When the jet stream meanders far south, it drags Arctic air masses deep into regions that historically experienced mild winters, hence the brutal cold outbreaks that have hit the southern United States in recent years, including the February 2021 winter storm that left large parts of Texas without power for days and killed more than 246 people, in a state whose power infrastructure was designed around the assumption that temperatures that cold simply didn't happen there. When the jet stream meanders far north, it allows warm air to surge into Arctic regions and blocks the normal flow of weather systems, creating the persistent high pressure blocking patterns that generate the heat domes we discussed, the drought conditions that bake agricultural regions for weeks, and the flooding events that occur when weather systems stall over one area and dump extraordinary amounts of rain. The consequences for agriculture are playing out right now across the breadth of the northern hemisphere's food-producing regions, and they are not confined to a single country or a single crop. The North American grain belt, the region that produces the wheat, corn, and soybeans that feed much of the world, is experiencing a fundamental shift in the reliability of the seasonal weather patterns that agricultural planning depends on. Planting windows, frost dates, rainfall timing, summer heat accumulation, the entire calendar of agricultural decision-making is built around historical climate norms that are increasingly obsolete. When those norms shift, not just in one direction, but in ways that increase variability and unpredictability, more extreme droughts in some years, more extreme flooding in others, late frosts followed by early heat waves, rainfall that arrives in shorter and more intense bursts rather than the steady distributed precipitation that crops can actually use, the economic consequences ripple through commodity markets, food prices, rural communities, and ultimately every household that buys groceries. The 2012 North American drought, driven partly by a persistent blocking pattern in the jet stream that parked hot, dry conditions over the agricultural heartland for months, reduced corn yields by approximately 13% from the previous year and drove corn prices to record highs. The drought affected approximately 60% of the contiguous United States and was the most widespread drought since the 1950s. Insurance claims from agricultural losses exceeded $10 billion. Livestock producers in affected areas sold off herds at losses because they couldn't afford feed. Rural communities built around agricultural economies saw their economic foundations shaken in ways that took years to recover from, and the atmospheric pattern that drove it, a slow, meandering jet stream creating persistent blocking, is exactly the pattern that Arctic amplification is making more common. In Europe, the consequences of disrupted jet stream behavior have been equally severe and equally costly. The European summer of 2018 brought simultaneous drought to northern Europe. Sweden experienced its worst drought in decades, with wildfires burning inside the Arctic Circle in a sight that shocked the world. While parts of southern Europe sweltered under heat waves, the following winter brought extreme cold outbreaks driven by a sudden stratospheric warming event, a disruption of the polar vortex, the large-scale circulation of cold air around the Arctic, that sent Arctic air masses plunging deep into Western Europe. The pattern of simultaneous extremes, drought here, flood there, heat wave adjacent to cold outbreak, is the signature of a disrupted atmospheric circulation, and it is a signature that Europe's agricultural sector, water management systems, and energy infrastructure are struggling to adapt to. The Mediterranean basin, home to some of the world's oldest agricultural traditions and to economies deeply dependent on predictable seasonal rainfall, is drying out. Climate projections for the Mediterranean consistently show decreasing annual precipitation, longer and more severe droughts, and more extreme wildfire seasons as atmospheric circulation patterns shift in response to both direct greenhouse warming and the disruption of the jet stream driven by Arctic amplification. The olive groves of Spain and Italy, the wheat fields of Morocco and Tunisia, the vineyards of Greece and southern France, these are agricultural landscapes built over centuries around a specific climate regime that is now changing within a single human lifetime. The economic displacement for communities whose identities, livelihoods, and cultural practices are built around these agricultural traditions is profound and largely invisible in international weather coverage that focuses on dramatic events rather than the slow erosion of climatic conditions. Yet in Asia, the story centers on the monsoon, the seasonal reversal of atmospheric circulation that brings the rains that support agriculture and human life for billions of people across South Asia, Southeast Asia, and East Africa. The Indian summer monsoon, which typically arrives in Kerala in early June and sweeps northward across the subcontinent over the following weeks, delivers approximately 70 to 90% of India's annual rainfall. The timing, intensity, and distribution of monsoon rainfall is the single most important determinant of agricultural outcomes for a country of 1.4 billion people, the majority of whom still depend directly or indirectly on rain-fed agriculture. Disruptions to the monsoon's behavior, late arrivals, early withdrawals, uneven distribution with some regions receiving catastrophic floods while neighboring regions experience severe drought, have consequences that extend from individual farming households to national food security to global commodity markets. The evidence that Arctic ice loss is influencing monsoon behavior comes from research showing that the reduced temperature gradient between the Arctic and the tropics, the same mechanism disrupting the jet stream in the northern hemisphere's mid-latitudes, also affects the large-scale pressure patterns that drive monsoonal circulation. Warmer Arctic temperatures in late winter and spring appear to be associated with weaker and more erratic monsoon behavior in subsequent summer months. The research is still developing, the mechanisms are complex, and the monsoon involves atmospheric dynamics that extend well beyond the Arctic's direct influence. But the pattern of increasing monsoon variability, more extreme flood years, more extreme drought years, less predictable onset and withdrawal, matches what the changing atmospheric circulation driven by polar warming would predict. The human geography of monsoon disruption follows the same brutal logic as every other dimension of climate-driven weather change. The communities most dependent on reliable monsoon rainfall for their survival are the ones with the fewest resources to buffer against variability, the least access to irrigation infrastructure that could compensate for failed rains, and the most limited capacity to recover from the economic losses that a bad monsoon year delivers. A drought year in the Indian agricultural heartland doesn't mean inconvenience for urban middle-class consumers who notice slightly higher vegetable prices. It means ruined harvests, debt that cannot be repaid, land that gets sold to cover losses, and families that migrate to already overcrowded cities because the rural economy that sustained them for generations no longer can. The human displacement driven by climate-disrupted weather patterns is already one of the largest sources of internal migration in multiple countries, and it is accelerating. Now shift attention to the Antarctic and to a dimension of its changes that receives less media coverage than Arctic ice loss, but that carries consequences for weather patterns in the southern hemisphere that are already reshaping economies and communities from Australia to South America to sub-Saharan Africa. Antarctic sea ice, unlike the land-based glaciers of the ice sheet, this is the floating sea ice around the continent, showed a pattern in the satellite record that was initially somewhat reassuring to climate communicators. For several decades after satellite measurements began, Antarctic sea ice extent was actually increasing slightly, which some skeptics of climate science pointed to as evidence that things were more complicated than climate models suggested. Scientists explained that the slight increase was consistent with climate model projections that accounted for the complex dynamics of southern ocean winds and freshwater input from melting glaciers, and that it didn't contradict the overall picture of human-caused warming. Then, abruptly, in 2016, Antarctic sea ice began declining sharply. The years since have seen Antarctic sea ice extent crash to record lows with a suddenness that surprised many researchers. In 2023, Antarctic sea ice extent reached levels so far below previous records that scientists struggled to find adequate language for how anomalous the situation was. At its annual minimum in February 2023, Antarctic sea ice was approximately 1 million square kilometers below the previous record low, an area roughly the size of Egypt, simply missing from where ice had been in every previous year of the satellite record. The causes are still being actively studied, but the consequences for southern hemisphere weather are being felt in the same way that Arctic sea ice loss affects northern hemisphere patterns, through changes in the temperature gradients that drive atmospheric circulation. Australia, whose agricultural sector and water supply infrastructure are critically dependent on predictable seasonal rainfall, has been experiencing the consequences of southern ocean and Antarctic changes. in ways that are economically devastating. The Millennium Drought, a 13-year drought that affected southeastern Australia from 1997 to 2009, drove water storages to critically low levels, devastated agricultural communities, forced permanent changes to water management policy, and cost the agricultural sector an estimated $6 billion. It ended, but similar drought conditions have returned repeatedly, and the underlying trend of decreasing cool season rainfall in southwestern and southeastern Australia, driven partly by changes in the southern annular mode, the dominant pattern of atmospheric variability in the southern hemisphere, points to a future of persistent water stress that the country's water infrastructure was not designed to manage. The insurance sector in Australia, as in the United States, has been repricing climate risk at a pace that is straining communities. Flood insurance in many parts of Queensland and New South Wales has become either unaffordable or unavailable. Properties that experienced once-in-50-year floods in the 1990s have experienced multiple major floods within a decade, as atmospheric circulation changes drive more extreme rainfall events. The financial mathematics of insuring these properties at actuarially sound premiums produces numbers that low and middle-income homeowners simply cannot pay. When private insurance retreats, the financial risk doesn't disappear. It concentrates in the hands of governments and individuals who are least equipped to bear it. Back in Kansas, our wheat farmer doesn't need to understand the details of Arctic albedo feedback and jet stream dynamics to know that something fundamental has changed. He knows it in his body, in the accumulated years of planting decisions that used to work and now don't, in the conversations with neighbors who are selling land that has been in their families for 4 generations, because the economics of farming a climate you can no longer predict have become impossible. What he needs, what all the communities living on the front lines of disrupted weather patterns need, is not just scientific explanation of why their world is changing. They need the infrastructure investments, the agricultural adaptation support, the water management systems, the financial instruments, and the policy frameworks that acknowledge the reality of what is happening and respond at a scale that matches it. The ice at the poles is not a distant abstraction. It is the thermostat and the weather engine of a planetary system that human civilization built itself around. When it changes, when the reflective white surface that moderates polar temperatures shrinks, when the cold water pouring off melting glaciers alters ocean circulation, when the temperature gradients that drive the jet stream and the monsoons and the southern annular mode weaken and shift, the effects do not stay at the poles. They travel through the atmosphere and the ocean on timescales of weeks and months and seasons, arriving as changed rainfall patterns in Kansas, as unreliable monsoons in India, as unprecedented droughts in Australia, as floods in places that have never flooded before, and droughts in places that have never run dry. Nobody built their farm, their city, their water system, their power grid, or their insurance policy for this weather. That is the true scale of what polar ice loss means for human civilization. Not the melting itself, the consequences of the melting spreading outward through every system that humans depend on, arriving faster than those systems can adapt, in communities that were never told this was coming and are discovering it now in the hardest possible ways. The ice is already gone that would have kept the weather predictable. The question that remains is whether we will face what its absence means honestly enough and urgently enough to protect the people who are already living with the consequences.